Hey guys, wanted to do a quick video on the PM-25 CNC conversion. This is with LinuxCNC and the Arizona Video CNC kit. I'm going to start off from the top here. The Arizona Video kit can't say enough good things about it. Went on really easy, it's pretty much bolt on. The one thing I was concerned about was how in the world am I going to incorporate speed control, and so I came up with the servo upgrade here. Also the pulleys was another thing I was worried about because I didn't have a way to machine out pulleys at the time. I was having some concentricity problems trying to use the CNC to machine new pulleys, so I ended up 3D printing them. These have, I want to say, probably under 100 hours, but I mean they've been really resilient to high RPM, long machine time. So both of them are 3D printed. That one's got a flange on it on the back there. It's a little hard to see, but yeah, that was a major cost savings in terms of having another shop try to produce a pulley on a lathe for me to get it concentric. The 3D printer, I've got a Prusa, was able to print these out reasonably well, and I'm running two timing belts. These are the, as you can see there, 3M 423 millimeter timing belts, just two of them stacked. You can get some wider ones, but they're usually on back order, so just stacked two. I've never had a belt slip. I've been running one, and I think the larger diameter pulleys help with that a little bit. So yeah, I can't say enough good things about this kind of setup. And there were a few different ways of doing this. I've seen fellas go with more expensive servos and a similar setup with stacked flanges, but all this is just two aluminum plates and then the 3D printed pulleys. This is a shoulder bolt, so it has a pivot on there. I'll probably post this on GrabCAD if anyone's interested. It's set up to use the really inexpensive Chinesium servos. This is a 2 horsepower Bergera, I think is what it's called, but you can find these for anywhere from $300 to $500. I haven't had any issues with belt slippage or this thing stalling. You can, it does lock when you first start it up, or it does engage, I should say, when you first start it up, so the spindle will freeze up. I'll show you here in a minute, but it works great for power tapping. The actual tap will spin in the holder before you actually stop the motor, yeah, it's been a pretty good setup. So moving on down here, I don't want to focus too much on the spindle upgrade, but we've got mist coolant. So this is just a little adapter plate. I didn't want to drill too many extra holes in the machine, so this is just where that little guard was mounted for the on and off switch for the controller, which was right here. The old controller I just took off and threw away once I got the servo attachment done. I was a little concerned about where I was going to mount my homing switches, which you definitely need. I was actually thinking about not using homing switches, but you absolutely need them. Otherwise your soft limits won't be set in LinuxCNC. So this is what I came up with. Just got a hole for oil bottle, and this bolts on to the carriage stops, and it has a little metal tab in there that will actuate the switch. Drilling and tapping the column wasn't too bad. You should go smaller in terms of drill size. This is really brittle cast iron, so if you've never tapped cast iron, just run the drill bit a little bit smaller and then run your tap in, and it should be fine. You can get a nut through the column itself for this particular Z switch, so if you do mess up, you can get a nut in the back of it through the hand wheel port here. Speaking of, This is a little adapter bracket I made. This is a Chinesium monitor arm you can get off Amazon for 30 bucks, but I wanted to have the controller on the actual machine. I used to have it set up on the desk here where it was turning and having to look and turn and pivot my chair, so this works out quite a lot better. So we're using LinuxCNC. This is the QT Dragon interface. Haven't had any problems with it. The probing routines work pretty well, but I tend to be pretty basic on the type of probing that I do. Probing setup on this is actually incredibly simple. I was actually astonished when I started to get into it. So I got the pretty basic $70 Chinese probe, and really all you need is just a single wire that comes with the unit. So this is the probe wire. It's a USB-C cable that they've provide with it, and it's long enough for my application where I bring it on down to the Mesa board. But this it just goes into your desired pin. You set up your pin setting on the point and click configuration wizard, and then you specify in your machine config that you want to use the Mesa the VESA probe, and it'll pop up this window and you've got all your different probing routines. So it is very powerful. You can do inside tubes and on edges. I primarily use this one here, what I'm referencing stock. In conjunction with the TTS system, it's actually very useful. You set up so you can where is that probe? So you can probe your Z position. You set, I usually run a G49, probe my height so the probe will actually come down, probe off your workpiece in this case, and then it will back off the specified height. And then from there you can say, from the top of the spindle to the face of the work is your measured distance of your actual tool. So in that case it's the tip of the tool plus the travel offset distance to the face of the TTS holder here. So you can go about measuring that. This works out to be roughly 4.5 inches. I measured exactly, but roughly 4.5 inches, and then you can measure each of your tool lengths and then set that up in the tool table. So you've got different holders for your your 3/8 end mills. So when you do a tool change, it's a manual operation. You pop this in, and then the tool height setting is picked up from the tool table. So it's pretty straightforward, and it's pretty handy. So the probe in conjunction with the TTS system is what I've been running. You can set this up with a tool height setter. So if you want to use something like R8 collets and save a little money on the TTS system, which is expensive, it runs you a couple $100. I probably spent like $400 or $500 on it. So if you want to run that, you can run one like out here on your table, and then set your tool heights that way. But that's a little more configuration to get into than I was willing to, and I kind of like the convenience of the TTS system. So yeah, that's what I went with. Moving on down to the table here, we have these weight covers I came up with because I was worried about dropping things on the table. As you can see, I'm dropping an end mill or something. So it keeps the table clean and clear of chips and things for the most part. I mean, it's not the most airtight cover. It's just got a piece of sheet aluminum with some magnets and kind of covers the table up when I don't have an extra vise on there. Just usually primarily keep one vise on there, but I've got an extra one in the closet there. These are some parts that I made on it so far. So this is a project that I've been working on. Got some really small, intricate features. But yeah, this is the kind of stuff you can do. I've machined titanium on this thing, aluminum, steel. This is a piece I was using to diagnose runout. So you can see the numbers on there. That's 1 inch 744 thousandths, 1 inch 746, so on and so forth. So I was using a snap gauge to see what my backlash is for each of the given axis as it was doing a circular mill through this, and the surface finish came out pretty good. and the tolerances came out pretty good. So this is after I got it dialed in. One thing I will note about the actual install with this, speaking of backlash and run out, is the y-axis I was having a little trouble with. So when I first installed this, I didn't get the actual coupler tight enough to where this wouldn't wobble. So what I would recommend is, with this latest design, is after you install this and you get your gib set back up correctly, you want to pull or push the Y out, so this is hanging out free in open air, and then get it tight enough to where you can't wiggle it. And a little tighter is generally a little better. And then once you get that snug, slide everything back into place and then put your bolts on. That was one issue I had with this. The second issue I had that was causing me a lot of backlash and run out problems was the Y nut, which is under here. So there's that aluminum block that clamps onto the saddle, and that has a single bolt that brings it up tight up to the bottom of the saddle, and that bolt is right here under the table. Now in my case, that hole wasn't either cut deep enough, and or the screw was maybe just a few thousandths too long, and it was preventing that piece from pulling all the way up flush to the base of the saddle, and that was causing some run out issues. So keep an eye out for that if you do happen to buy one of these Arizona Video CNC kits. I mean, Dave is he's just one guy making them, so you might miss a thing or two. So, do your due diligence and be aware this is gonna take some debugging. On the front, I do have my X and Y limit switches. I tried to be as non-intrusive to the actual machine as possible, so this is mounted up on existing bolt holes. I can't quite remember what's there. I think there's like an indicator there for your tape on the table. So if you want to keep that, you'll have to choose a different spot, but this works for me. And then here I drilled and tapped some new spots. So this is again on the saddle locks for the Y-axis, and it's got a little tab under there, kind of a common theme. I machined these by hand when I was getting the waiting for the kit to come in, so I don't really have CAD for these. I just kind of made them up on the fly, kind of just pounded away on them until I got the shape that I wanted. So there's no real definite angle, just kind of what works, and you can slide that little shoe, I guess you could call it, a little ramp piece back and forth to get the on and off actuation that you want. And yeah, it works pretty well. I've seen some other configurations with some like magnetic sensors and other things, but I like switches. These are Chinesium switches you can buy off Amazon. You can kind of see the name there, if you will. So they came with really long leads, which I like, and they weren't too expensive. I mean, on McMaster-Carr or something, these are like, I don't know, $50 a piece or even more for some of the switches. So yeah, definitely a decent deal. These are closed loop NEMA 24 steppers. I went with the NEMA 24s. I've never been able to stall them during cutting. Not that you want to. You can run them up to 100 inches a minute with LinuxCNC. I tend to keep things down to 60 inches a minute when I'm jogging, just to not go too fast. I mean, this is a small machine. You're not going to be rocking it like a Haas or something. So try to keep things reasonable when you're cutting. The fastest I've ever cut on this probably would be about 20 inches a minute, but that's with aluminum. I mean, with titanium and stainless and steels, you're slowing down a bit. It doesn't have all that great of rigidity, but you can plow away on some stuff if you really dial in your feeds. You've got a good sharp cutter, and I tend to use the Speed Tiger cutters that you can find on Amazon, so it's not too expensive, and you can buy one for a couple bucks. So, and they do tend to last on various materials. I decided to mount up the electronics package, or the control box on the side here, primarily because I put the e-stop in that position. If I hadn't, I would have probably routed it around to the back. That might change one of these days if I ever feel like taking this damn thing apart, but yeah, for now this is where it's going to sit, and it seems to work just fine. Got all the different stepper motor, encoder, and drive cables all partitioned out. The servo was a little tricky. This is the largest enclosure that I could find on Amazon. It's just plastic. I didn't want to have to deal with cutting into metal or buying some punch outs. So it's pretty basic design. Probably not the best out there, but it's what I came up with. So from top to bottom here, we got servo, got our NEMA 23 X and Y, and then the Z. This is a NEMA 34, and then we've got the the Mesa board here. So this is designed. You've got your AC side on this side, and yes, I know those probably aren't the correct distribution blocks for this, but whatever, it works. Going up to the servos, down to the power supplies. This is your DC side, going up to all the steppers, and there's an independent power supply stuck down here for the Mesa board, so that I can shut off the servos and the steppers without shutting off power to the Mesa board. That's kind of a design decision that I made. I didn't want to have to constantly mess with networking, which it is not a big deal, but do keep in mind that if you start sending commands to this thing the way I've designed it, and you turn on the steppers, it will kick off and start moving in whatever direction you said to go. So that is kind of a design consideration. Then you've got just a AC fan down here, and I drilled some vent holes up there. Due to the way this is sealed, I haven't had much intrusion of chips or dust or anything. It pulls from the bottom and then pushes air out, so it's not going to suck anything in. So that's been pretty good. These are sealed up top, so kept the dust down pretty well, and I always keep this closed when I'm running it, but so not too bad. Let's see if we can close it up here one-handed. Oh, might have to, there we go. There we go. See if I can get at least 2 latches on. Let's start it up here. So, start up, starts the fan, turns on the encoders. Go ahead and get my parts out of the way here. Speaking of the configuration of the Bergera servo, so this is programmed to run by default at the factory at 2,500 RPM. You can get it to go faster, but you do sacrifice torque, and you do sacrifice a little bit of stability. I say read the manual. It's a decent translation from Chinese to Chinesium English, so I figured it out. It shouldn't be too hard to figure out. The one trick was that once you set the new RPM range, there is an option where you have to essentially save or post that change to the controller. Otherwise, when you power it off and power it on again, it will forget, and it will lock you back into that factory 2,500 RPM. I run this before at 3,000. Cutting aluminum, and it's worked just fine. The beauty of the 3D printed pulleys is you can go into SolidWorks and print smaller or larger diameter pulleys on either side to get different RPM ranges and different torques. And so it's a phenomenal system, and it's incredibly cheap to print a pulley for less than a couple bucks. So I've been really thrilled with how that came out. If you may have noticed, this is a captive nut, so it has a set screw in there that's recessed, and there's a quarter 20 bolt on the inside of the pulley that holds it on. Same with this side here on the motor side. The motor is now on, so it used to be that you could stall this with the 1 horsepower that comes with it, but with the 2 horsepower, I'm wrenching on it pretty good here, and it barely moves. I mean, the limit here is the actual spline shaft, the fit there. So it has a tremendous amount of torque now, and it's not to be trifled with when you actually start it up. So for a homing procedure, this machine's designed to, see if I can get it to go home here. Normally it stays home, and it's going to ask if I want to rehome or unhome the axis first, and then it's going to go to home on all the axes. You do have to be careful. Sometimes I've caught myself cleaning the machine off or something, and I'll bump a switch. You'll see here in a second that it's going to go back to the program position. So if you do have your switches in this location, you have to be very standoffish and not touch anything or even tap those switches, because it'll try to search for its home position and just not stop. So for example, like if I just touch that switch now, it's going to go back the expected distance to its home position and crash the machine. Crashes aren't too bad with this. I've done that by accident, where I'll tap this machine, or tap the home button, and it careens back and locks itself out. I've been able to restart LinuxCNC so that it's not trying to continually home itself, start the machine back up again, and then back it off with a stepper. Worst comes to worst, you could pull the stepper off and then back it out, but you'd have to try very, very hard to bend the lead screws for this. If you can see on the website, but these are really nice double nut ball screws that the Arizona Video CNC kit comes with. I mean, in terms of quality, this kit is just absolutely phenomenal in terms of design, and he keeps updating it throughout. So it's a very good kit. So we are home now, and let's see if I can start up the spindle here. Let's go to 2500 RPM. Let's see if I can punch buttons and hold the camera. There we go, 2500. So there's 2500. So not too bad. And then you've got your spindle stop here. And the beauty of the QT Dragon interface is that it actually obeys your acceleration curves for the spindle. I found that the Axis and the GMO Cappy interfaces don't really obey that very well. They tend to stop the servo on a dime, which this thing, it's so powerful that it can go from 0 to 2000 RPMs almost instantaneously. I mean, it's not really instantaneously, but you get the idea. It is very, very fast. So yeah, that pretty much covers it. The stand is pretty much stock. Oh, by the way, the spindle, or the mist coolant, this was actually a cheap eBay version. This is the the sucky version. So I didn't want to spend a full, I don't know what is, like $300, $400 on the Cool Mist official version. So I found the eBay special for $14, and it's been running just fine ever since I installed it. The actual coolant is down here. This was a tank, the 1 gallon plastic tank that I found off of Amazon for, it was less than 20 bucks, probably about $10. So I mean, for $25 to get a mist coolant system set up, all you need is just air and the mist coolant line. So this is your liquid, this is your air, and that's run back to a compressor behind that wall. So it is a really compact package, and I don't have a lot of room to work with in here, where I'm situated with my shop. So yeah, it is quite a powerhouse for what it can do. I've machined a lot of hard to machine materials. I mean, titanium is one of my worst enemies, but you're able to do some pretty cool stuff with it. So if you guys have any questions, let me know in the comments. I'll be sure to post the servo design up on GrabCAD, and put the link in the description if anyone's interested. And yeah, thanks for watching.